In this video, I'd like to address the following question. I have a rigid body and it is pivoted at point P. The point C is the center of mass of the rigid object. So gravity acts through that center of mass. Now in the previous video, you saw the period of a physical pendulum was derived there. So let me write what we had from that previous video. The frequency of simple harmonic oscillation of a physical pendulum, that would be the square root of the acceleration due to gravity times the mass times this distance between the pivot and the center of mass, which I will call D, divided by the moment of inertia about the pivot point. Now from that period, the period can be got. The period T simple harmonic is given by 2 pi divided by omega simple harmonic. So I can write the expression for the period. Now in this video, I want to ask a slightly different question. Suppose you have a choice as to where to place the pivot. So you have a choice. You can drill just one hole in this rigid body, and once you drill that hole and you pivot it, the period of oscillation is the shortest possible. The period is defined as the time taken to go back and forth once. So how do you find the minimum period of oscillation? Now for this analysis, I'm going to take the distance to be the variable. So I'll call the distance between the pivot point and the center of mass x, because it's now a variable, and I'll write the period as a function of x. It's going to be 2 pi square root of the moment of inertia about the point P. Now the moment of inertia about the point P by the parallel axis theorem is the moment of inertia about the center of mass plus md squared, or in this case mx squared, divided by mg times x, where I sub c is whatever it is for the rigid body. It's a standard result. You can get the standard result from either a table, or you can work it out separately as a side calculation. I'll just not worry about that for this particular problem. We are mainly concerned with making this t a minimum value. So the square root, and then you have a fraction. You can see the calculus is going to get pretty messy. But here's the thing. Instead of minimizing the period, let me try to minimize the square of the period. So I'm going to define a function, f of x, and this 2 pi, I don't really want to see this 2 pi or this mg here. So what I'll do is I'll define this function f of x as follows. I'll define it as t simple harmonic squared divided by 4 pi squared, and then let's see if I can bring an mg here. That'll get rid of that mg. All right, let me define the function like that. So then if I make the substitution, so if I square this, the 4 pi squared will cancel with the 4 pi squared. The mg downstairs will cancel with this mg, and I'll be just left with I sub c plus mx squared divided by x. All right, that's not a bad function to think about. We can differentiate this because this looks like the ratio of two functions, which I'll call h of x and g of x, and we can use the quotient rule. So f prime would be, the quotient rule goes like low d high minus high d low divided by low squared. So let's find out what it is. gh prime, h would be the entire top part, so that's x times, if I differentiate the top, I'm going to get 2mx minus h, which is that expression, times the derivative of the denominator, which is just 1, divided by the denominator squared, and that has to be set equal to 0 for extrema, be it maximum or minimum. So let's try to solve this. That's 2mx squared minus I sub c minus mx squared equals 0. The denominator does not matter. It's just the numerator that needs to be set equal to 0. Because of this negative sign, it is possible. So what I'll do is I'll subtract one of the mx squareds and take the I sub c to the other side. So I'm going to get mx squared equals I sub c. And then I have my optimum value. X is equal to the square root. The critical value is the square root of I sub c divided by m. Okay, and that's the critical value at which you get the minimum period. Now, to show it's a true minimum, you have to differentiate again. But think about it like this. It cannot be the maximum period. Okay, if you have an extremum, it can either be the minimum or maximum in a physical situation. It cannot be the maximum period, but because the maximum period is got by pivoting it to the center of mass. Why is that? Because then it hardly moves. It never moves. It just stays where it is. So that's the maximum period, which is infinity. So this has to be the minimum period. You can use that argument if you like. Now, once you have the minimum period, you can go ahead and substitute it into that formula to find the minimum oscillation. Once you have the minimum value of x, you can go ahead and substitute to find a minimum period, and we'll complete the problem. So let's do that. The minimum period min at this value x min would be equal to 2 pi times the square root of I sub c, plus when I take x squared, I'm going to get I sub c over m, and that m is going to cancel with the m here, so I'll just get plus another I sub c divided by mg times the square root of I sub c over m. So let's see if we can simplify this a little bit. This is going to be 2 pi square root I sub c plus I sub c is 2i sub c, and then here I have a square root of m because of the square root of m here cancelling with m times g square root of I sub c. So simplifying it some more, I get 2 pi times the square root of 2 over g times the further square root of I sub c over m. So that's our answer for the minimum period. So we have completely solved this problem. You poke a hole through the physical pendulum at this point, at this distance from the center of mass, and when you do that, the minimum period is going to be precisely that. Let's take an example of this problem for a rod. So I have a thin uniform rod. Let me draw a picture here. It's uniform in the sense that its cross-sectional area does not change as you go this way, and it's very thin, meaning that the diameter is much smaller than the length, so we don't have to worry about the more complicated formula when you pivot it about some point. Let's call that point P, and the center of mass is somewhere in the middle because it's uniform, and this distance x is now going to be that. Now for a rod, the moment of inertia about the center of mass is 1/12 ml squared, where L is the length of the rod. So let's use this in this formula and see what we get. X minimum would be the square root of I sub c divided by m. So the m's will cancel out, and I get L squared over the square root of 12. L, just L over the square root of 12. So that's a interesting result. Now let's substitute it into this formula and find the minimum period, T minimum. So let me try to evaluate this, and here I'm treading on ice because I'll have to do this by sight. 12 is 4 times 3, so that's 1 over 2 root 3. And 1 over root 3 is root 3 by 3, and root 3 is 1.73, so that's going to be 1.73 divided by 3, which is 0.58, and 0.58 divided by 2 is something like 0.26. Something like that. So something like 0.3, approximately 0.3. So you have to place it 30% of the length from the, so if this is a meter stick and this is a 50 centimeter mark, this has to be placed at the 30 centimeters away from the 50 centimeter mark. In other words, 20 centimeters from the top is where you would find a meter stick's optimum position for poking that hole. Now, what's the minimum period under those circumstances? It can be found by using this formula. It's 2 pi square root of 2 over g, and you again have this I sub c over m, which is same as x min, by the way. So I can simply substitute that here. So it's 0.3 L being crude. Now for a meter stick, L is 1 meter, so I won't even bother writing it. So that's going to be 0.6 in the numerator. Denominator, you have the acceleration due to gravity, which is 10 approximately meters per second squared. So that's going to be 2 pi. Now what I can do here is write this as 6 over 100. So that's going to be 2 pi over 10 times the square root of 6. So it's what it is. It's something like that, seconds. And what I did for the meter stick, you can repeat for any other object. You can try the ring. So some of the things that you can try at home, try for a ring pendulum, the disc pendulum, and I'll ask you to think of other things on your own. You can find out where you should poke this pivot hole to pivot them so that you get the minimum period of oscillation, and also what that minimum period of oscillation is.